Okay. I think just to make sure, confirm next week we'll have the interview then. I would like to take your time in exercise, especially the one that I did. We are not really discussing that exercise today, but I will let you know whether we will have some additional information on, for example, because I think I will take that exercise as a reserve for your, if your maybe midterm is not really that good. I can have those exercises to be uploaded as homework to add your points. Okay? So I think that will be the case. So I suggest to have you get in your exercise, that exercise in the middle. I'm planning to give you a couple of questions, but not the same as the exercise, but maybe similar subject. Okay, and because I think we have I need to make sure with the chapters, with which chapters we are going to deal with in the at least for next week or next 2 weeks. So I need to give you some basic introduction first about the next chapter. Just a few bits. Okay, what kind of sections that we are going to discuss. Okay? It is about the Laplace transformation. Okay? So the chapter 1, 2, 3, they are differential equations. This chapter 4 is actually continuations from this differential equation. So it's more like how to set up some transformation that can transform your differential equation into an algebra. So let me give you just introduction or just a basic principle at the beginning. Okay, and we can continue this Laplace next Thursday. Okay. Okay, to begin, consider, let's say we have x squared like this. If we take derivative, okay, take d dx of this x squared, we now have the 2x, right? And if we take the, let me write x squared, take the integrations, then we have the dx. We have 1 over 3 x cubed plus constant, right? And if we take the, for example, take some number, let's say from 0 to 3, okay, of x squared dx, we can plug in the 3 inside, and we have 27 over 3. It's 9. Okay, we have all this. We can say that this is also transformation. We transform the functions into another function, actually, right? We derive, we integrate. This is actually a transformation. This is a transformations, also transformations. And this is what we call with linearity property. This is what we have in our discussion before, that we have the differential operator, that we have the linear property. We can write down like with capital D or capital L to say that, okay, this is the linear operators of the differential equations. Okay? And of course, from this linear property, we could have the property that you already learned in calculus. So I don't really need to review that part. Okay? But what we are going to talk here is okay. Okay, let's say we have an integration from some point A to point B of some k, let's say k, a function, and it has two variable s and t, and then another function t, f with a variable t, and we integrate this with dt. Remember, when we deal with the, I believe the chapter 2, the first order, when we have the exact equation, if you remember, we can have somewhat an integral, but it has two variables inside. Right? For example, if we take the dx, it means that we treat the y as a constant. Right? We treat y as a constant. Okay. So similarly, when we have these two different positions that we want this to be able, so we can transforming f of t into function of s. Okay. So of course, to make this happen, we need to have an interval. Let's say the interval is from 0 to infinity. And we need to take this and take the limit, because we have the unbounded interval. We take the limit and maybe take b as the interval for the infinity. So b, 0. And we need to say that the limit for the result to be exist, the limit should be exist. The limit exists. Then we say in the calculus we already learned in the improper integral that this will be convergent, right? If it doesn't exist, it's divergent. And now the question is, to make sure that we can let this to be true, or we can make the limit exist, we think what kind of functions that we can take for k, and we can apply any functions. But if you remember, the one that really take some significant impact in the differential equation is the exponent. If you remember the exponent, if we derive, it's still the e. If we integrate, it still has the e. Okay. So perhaps the e will be a better choice to take this k. So k will have s and t as its variable, but within the exponent form. Okay. So we could see, if we take the choice that k is e with negative st, this will give us a new perspective on these integrations. Okay. Okay. So let f be function defined for t greater equal 0. Then let me write with the blue color. The definition for the Laplace. Okay, I will give you definition first and give you later what is the consequence within these definitions.
The Laplace is, to write Laplace like that, this is the symbols of Laplace. Laplace of the function of t, which means
this is our function that will be transformed. Laplace is the tools to transform it. But the Laplace itself
is defined by this integral. Okay, so this is, let me write, is said to be Laplace transform. Laplace transform of f, provided integral converges, which means the limit
at some n or b going to infinite, it's going to be converted by a6.
So let me write some notes before we give you some proof and more examples. So notes for the Laplace is Laplace will be useful for transforming differential equations into algebraic expression. Okay, this is actually our goals. Okay, it's supposed to be the last note, but I will give you this as in the beginning to help you to realize what this Laplace is actually means. Because in the differential equation, if you have like higher order, sometimes we feel that it's kind of difficult, and the method is actually quite limited. If you remember the method we have, like we have the constant coefficient, reduction order, and so on, they have their own limit, right? The weaknesses. So with Laplace, actually we can solve the differential equations, changing them into algebraic expression, and solve them as in algebra. That's the idea. Okay, I will stop this Laplace until here. We will continue this part next Thursday. So now we are moving to some question on chapter 3, the higher order differential equation. Okay. Okay, let me take some review. Okay, let me take the last part. Okay. Okay, let's begin for some couple of questions that I would like to discuss with you. So we learn in Cauchy-Euler equations how to find the solutions, right? But what if we could arrange the differential equation from the solutions that we provide that is provided. Okay. For example, let's start with the if y is equal c1 plus c2x with power of 5. Find homogeneous Cauchy-Euler differential equation, which means that maybe the complete question is, if this is the solution of the Cauchy-Euler, what is the differential equation? So you are now given the solution. This is the solution. Now you need to rearrange the differential equation. Now first you need to remember what kind of solution that the Cauchy-Euler has. You need to have the x with power of m. And what we have here, we have this c1 without any x, and c2 x with power of 5. So there should be x here, but it's gone because x is power with 0. Okay. Now let me give you a couple minutes. You can try first, okay, and then let's see how you can deal with that. I hope from the Cauchy-Euler introduction, you can reverse the process from the solution to the differential equation. Yeah, good. Good. Write some conclusion from those equations. Yes. Okay, I think should be able to see the pattern, right? So first thing is imagine let me write the solution here. So the solution should be in the form of x with power of m, right? So in the first constant one here, it should be some x with power of m. So we could say that the m, let's say m1 is supposed to be 0. And the m2 is 5, which means that we have our m and then m minus 5 as our equations for the auxiliary equation in Cauchy-Euler. Okay, so this is supposed to be 0. And we have m squared minus 5m. And always remember that the structure of the Cauchy-Euler is going to be am squared plus b minus a m plus c. So from the structure, we could see b minus a c from our equation here, and we can determine, and then we can rewrite them and write the differential equation itself. Okay. Now we could determine from here that a is 1, b minus a is minus 5, and c is 0. Okay. So b is minus 5 plus 1 is minus 4, which means that we only need this a and b. So we could write down that it's supposed to be ax squared, right? And then it's supposed to be y double prime plus bx. Let me write this as just the normal forms. And then cy equals 0. So a is 1, so x squared y double prime minus 4y prime, and all is 0, so equal to 0. Okay. Okay, I hope this is not really a problem. Okay, so you could trace back the original differential equation from these solutions that are given. Okay. Yes. Oh, yeah, I forgot to write. I missed out 1x. Okay. Supposed to be 4x. Okay. Yes. Okay, now giving you another questions just to make sure and confirm the Cauchy-Euler can be understood. Solve Okay, I think it's quite simple for this part. First thing, every time you see any Cauchy-Euler, and you can identify this as a Cauchy-Euler equations, square, second order, linear, and then there's one differential, one first derivative, and then a constant is y. Then you could try to work out this as a Cauchy-Euler. And Cauchy-Euler, if, for example, the right part has another variable or maybe constant, then we could work out the Cauchy-Euler as our yc, okay? yc. And then for yp, still we need to solve within this right hand. We can use the variation of parameters or maybe the undetermined coefficient. But I think it's best pairing with the variation of parameters, my suggestion. But you can check other methods as well. So first is we can name all this part with ABC, and we could write our auxiliary equations for Cauchy-Euler. So Cauchy-Euler, so the same thing here. Okay, so we are writing this part here, same thing. So we write the am squared plus b minus am plus c is equal to 0. So write all the here. The m squared, b is -3, -1 is -4, and then c is 4, so plus 4. And this is can easily factorize with m minus 2 is equal squared equal to 0. So m1 equal to m2 equal to number 2. Okay, value is 2. And remember, when we have repeated roots in Cauchy-Euler, we need to multiply with the elements. Okay. So we could write down the solution is c1 x squared plus c2 x squared, but with ln x. Okay. But we have this expression here that we need to apply, and we need to find constant. Okay? We need to find constant. Complete our answer. So we can complete that with the initial conditions. So check out the when x equal 1, and this is 0, right? And this is supposed to be equal to 5. So c1 is 5. And then y prime, and then 1, or maybe y prime first. We could take the y prime as 2c1x plus c2. This will be 2x ln x plus x, right? And then y prime as x equal 1 is 2c1. c1 is 5, so we can take 10 plus c2. This is 0. This is 1. So c2 is equal to, this is equal to 3. So c2 is negative 10 plus 3 is negative 7. So the result is y 5x squared plus, or minus, sorry, 7x squared ln x. next part, okay, if you have taken notes, next part maybe some, okay, let's say y double prime minus 2y prime plus 2y equal to e x tangent x. You should be aware of the tangent. Okay? So whenever you have the second order or maybe higher order, and then you have a tangent at the right side, you need to be aware that maybe this one technique that can be applied. Okay? Remember, most of the techniques or most of the equations can be solved with the undetermined coefficients. You can check each one, but for tangent, secant, and for mostly the secant or tangent, they can be solved if we take the variation of curve. Right? So I think this can be all solved by variation of curve. So let's try to take that. But first, always take the homogeneous. Okay, we have the non-homogeneous here, right? So always solve homogeneous constant coefficient. How to solve this? We take the auxiliary equations. In our case, we are going to assume that it will have the e to the power of x, right? E to the power of mx, to be precise, and we need to find this m. How to find the m? We can imply m with this order as our degree, right? So we could take that as m squared minus 2m plus 2 equal to 0. And if you see that this is not a real complete solution, right? So we have an imaginary number in our roots. And remember, whenever we have a complex roots, then we need to imply the Euler relations, e to the x, and then we have the alpha, beta, okay? So let's try to check that out. We could take this plus 1 like that, and imply that so m is plus minus here, so it's 1 plus minus I. So we have m1 and m2 as 1 plus I, 1 minus I. So alpha is 1, beta is 1. So we could take that as our yc is c1 e to the x and then sine x, because there is nothing, no other constant, right? Alpha is 1, beta is 1, so plus c2 e to the x cosine x. Okay. And always remember that the complex roots, the template, all the same. What you need to do is just finding the alpha and beta. So now we could argue that we have y1 and y2. From this proposed y1 and y2, we could propose the Wronskian to take the variation of parameters. So we take these two as our Wronskian determinant. So we take the Wronskian and writing the y1 here and then y2 over here. Okay, so the next row is supposed to be the derivative of these two. So let's write the derivatives. This is ex, still ex sine x plus ex cos x. This will be negative ex sine x plus ex cos x. And then take the determinant, cross multiply, and minus this 2. Well, somewhere in between there will be some cancellations, I think. So we could take this. Let me just take this 2x sine squared plus e2x sine x cos x, and then minus. And then minus e2x cosine squared x. And we see that this will cancel, and we can look on this part that we can plus this 2 as and becoming 1, and we have the negative e with power of 2x. That's our Wronskian. Okay, which means it's not 0, and thus it's linearly independent. Okay, so another way to prove the linearly dependent is to take the Wronskian. So whenever maybe you're given function, like in your exercise, I give some function and you need to check they are linearly dependent or independent. One way to check is to Wronskian, or if you want to check, you can multiply with the constant and maybe take some arrangement, making it 0, or maybe take the first two functions and it has become the third function, and also dependent. But another way is just to take the Wronskian. So take the Wronskian, and then after that we identify the f of x is e with power of x tangent x. Now we apply Cramer's rule and try to check the u1 prime, or maybe let me write the w1. W1 is, we change all the first column with 0 and ex tangent x, and then this will be ex cosine x, and then its derivative. And we have ex cos x, ex tangent x. Okay. And we take the second one for W2. So ex sine x plus ex cosine x, 0 and ex tangent x. This will be ex sine x and ex. Oh, it's supposed to be minus the first one. Sorry, forgot to make sure that this is the minus sign right there. So ex sine x and ex tangent x. And then the u1 prime is w1 over w, the Wronskian. So minus ex cosine x, ex tangent x, like this, divided by negative e2x. So we can simply say that, yeah, we get negative cancelled, ex, and e with power of 2x is also cancelling all together. So cos x multiplied with tangent is the sine. So it goes to be sine x. Okay. think I need to make a little bit smaller around here. Let me resize this. Maybe go over there. Resize, go over here. Okay. And then U2 prime is W2. So EX sine X, EX tangent X divided by negative E to X. So we have a negative now. So sine X, tangent X, this will be sine squared X over cosine X. So negative sine squared X over cosine X. Or maybe we can well, we could take this 1 minus cos squared X to make the cos X minus secant X, right? We could write that. Because I think this will be, I think, better. We want to integrate. And then take the integrations. So U1 is integration sine X dx. Is negative cosine X. U2 is integration of cosine X minus secant X dx. And if you remember, I believe this will be sine X. The secant, if you remember our calculus, this will be ln secant X plus tangent X. But this is not the final answer. So we need to write the final answer in terms of y. So y, let me write y is u1 y1 plus u2 y2. Or this is the dyp. Okay. So u1 y1, where is u1 is negative cos X, multiply with the c, where is y1? Y1 is this, right? Okay, I think we can simplify. Okay, you could check the answer. So this will be c. Let me write y is yc plus yp. So yc is c1 ex sine x plus c2 ex cos x. And then we multiply all together with the yp. U1 is minus cosine x, multiply with the dx sine x. And then we have sine x, multiply with the ex cos x. And you notice that it's plus minus, so it's cancelled. So we only have the ln. Okay, so the sine and cosine in this part, they are cancelling, so we have only the last part. But you could just multiply, okay, and then check. I'm skipping some process here, just writing the final solutions. That is ex cos x ln secant x plus tangent x. Okay.
So I believe maybe let me review what we will have in the midterm, okay? And then that will be our last part for this. So the midterm will consist the chapter from the very beginning, the introduction to differential equations, classification on the types of the differential equation, the techniques that can be used to also, because sometimes the differential equations you can solve in many ways, and you need to classify, can it be solved within maybe exact equation in first order, maybe the Bernoulli, or maybe the separable linear, right? The other part is to tell the statement whether it is this it's true, the definitions. Okay. Maybe let me write in a new page, okay, to give you more clear explanations. Okay. So your midterm will consist at least the first order, the techniques, okay, the techniques, and classification. Okay, and this, the higher order this is mostly the first thing in higher order is to tell it's linear independent, right? Linear independent. The techniques, okay, the techniques we can have like from the very beginning, the reduction, right? And the constant coefficient, the constant homogeneous, and then the what else? The undetermined, the variation parameters, and the last part is the Cauchy-Euler. The Cauchy-Euler is actually an additional note, okay? Because without Cauchy-Euler you can also solve the equation as well, right? So I hope you can have more exercise at the end here, because maybe in one question, maybe you need to know the constant coefficient and maybe some other factors. I prepared maybe around 7 questions, or 7 questions probably. Okay.